Alright, welcome back ladies and gentlemen. This is section 5.3 of Statistics for Kellogg Community College. We're going to be looking over section 5.3, the binomial distribution, and 4 requirements of the binomial distribution. Alright, now the binomial distribution has a couple different parameters. First of all, binomial distributions have to have a fixed number of trials. So we're going to talk about a fixed number of trials. We're not going to run an infinite number of trials. We're going to talk about only a certain number of trials. And each trial can only have 2 outcomes. And we're going to call these 2 outcomes pass or fail. And obviously the words pass or fail is very dependent on what we're talking about. Now, each of these binomial distributions have to have independent outcomes. And finally, the probability must stay the same between trials. We can't change probability between trials. So if we're picking the odds of something to have happen, we can't change those odds in between 2 of the different trials. So we've got to have the same number of we got to have a fixed number of trials. Trials can only have 2 outcomes. This is why it's binomial, bi meaning 2, and independent outcomes. So one trial won't affect the other trial, and finally, the probability must stay the same between trials. This is all very good for good science and good data gathering. Now we got some notation to learn too. The probability of S is the probability of success. And we're going to have our small letter p be that probability of S either as a fraction or a percentage. So P is going to denote the probability of a success. Q is going to deal with P of F, which is failure. So Q is going to be the probability of failing, and that's either going to be a fraction or a percent again. And these fractions and percents have to be between 0 and 1, because they have to deal with the idea that there is a anywhere between a 0 and 100% chance of something happening. So for example, if success is 1/4, failure is 3/4. If success is 90%, failure is 10%. So they have to add up to the 100%. N is the number of trials. And X is, very carefully, this is the number of successes in the N trials. So it's the number of successes that you're looking for in your N number of trials. Now again, this word success doesn't always mean something good. So for example, if we're looking at how many people are dying out of a group, dying is a successful trial in that. And that seems very counterintuitive that you want that. But if you're looking for that, we have to be very careful about what we're calling success in each problem. Now here is the binomial probability formula. The binomial probability formula is n factorial divided by n minus x factorial times x factorial, which is, if you remember this from chapter 4, this is a combination. And this is then multiplied by our probability of success raised to the number of successes in n trial power, multiplied by Q raised to the power of n minus x. Alright, and we're really going to hash this out here. Right now this looks like just a mess of numbers, but as you do more and more of these problems, you're going to see like, oh, I see patterns here. So let's take a look at this here. It says the example is 1 out of 5 Americans. Now what I would do is I would seriously underline and circle the numbers here because they're going to be put into this problem here. 1 out of 5 Americans says that they had visited a doctor last month. So 20% visit a doctor. If 10 people are selected at random, Find the probability that 3 of them will have visited a doctor last month. So let's do a hypothesis here a little bit. So what we're doing is we're saying that about 20% of Americans visit a doctor each month. So what are the chances that 3 out of 10 or 30% actually saw a doctor that month? Do you think this is going to be likely or less likely? Because if we know that only 20% go see a doctor every month, what's your guess for a random sample of 10 people that 30%, higher than the 20% here, will actually have seen the doctor this month? And this is what the binomial distribution really lends itself to. So first of all, we're going to talk about n, the number of trials. Now we're picking 10 people at random, so n is equal to 10. X is the number of successes that we want in n trials, so that is going to be 3. Because we're looking for 3 out of 10 to have gone to the doctor. Now, here comes the probability. We're looking at how many, basically how many went to the doctor, so this is 1 out of 5. So here we go, 1 out of 5. And then those who didn't go to the doctor, well, that'd be 4 out of 5. Alright, now let's put all these in the mix. Our formula is n factorial divided by n minus n factorial, or sorry, n, I put that exclamation point there, n minus x factorial times x factorial, okay, multiplied by my probability of success raised to the x power, multiplied by my probability of failure raised to the n minus x power. Now I've done no simplification here whatsoever. I just wanted you to see where the numbers went according to this binomial probability formula and where things went here. Now let's do a little bit of simplification. Alright, so simplifying my combination here, this is 10 factorial divided by 7 factorial times 3 factorial. This is not, 7 factorial times 3 factorial is not the same as 10 factorial. Some people simplified that out on the last test. No, that doesn't work. Now this is 1/5 raised to the 3rd power, and then 4/5 raised to the 7th power. Now, I want to show you some cool synergies here. First of all, you'll notice that 3 and 7, that adds up to my 10. So you'll always kind of see those. Your 4/5 and 1/5, that will always, add up to 1. And you're going to see these patterns. Do these problems more and more, and you'll be like, oh my gosh, now I kind of see how things work. Now, if you copied all this down correctly into your calculator, and what I would do is take this step by step, go 10 factorial divided by 7 factorial times 3 factorial in parentheses, get the answer key, then multiply that 1/5 cubed, then multiply that by 4/5 to the 7th power. This gives you an answer of about 20%. In this study, we would have 3 out of 10 people going to the doctor 20% of the time. This is not very likely, is it? We only had 1 out of 5 going to the doctor. To say that 3 out of 10 are going to go to the doctor, not very likely. Hey, if we basically did the same thing and wanted 4 out of 10 or 5 out of 10 or 6 out of 10, this is going to go way down. So right now, if we want to look for better odds than what's actually happening, don't expect a high probability of that happening. All right, now we're going to do a couple more problems on the back here. All right, we're going to look at some dropout rates. Approximately 10% of American high school students drop out. We're going to choose 10 students at random and find out about what's the probability that all 10 will graduate. Okay, so n being the number of trials that we're looking at here. And the number of trials we're looking at is we're pulling out 10 people. So we're pulling out 10 students, so my n is going to be 10. Now, I want all 10 to graduate. Now, the way I would get all 10 to graduate is I would want 0 dropouts. Okay, 0 dropouts. So I'm talking about wanting 0 dropouts. Dropouts becomes my success. So my probability of success is 10%, because 10% is the dropout rate. So notice that I want 0 dropouts, so I have to consider this as my success rate for a dropout. Now remember how I said sometimes we have to think of success as being a bad thing? I want 0 dropouts, so I want a 10% to be modified by that 0. That means my failure rate is going to be 90%. And that's, again, it feels backwards, doesn't it? But the reality is I want to test my dropout rate. And I want 0 dropouts in my 10 subjects. So here we go. We're going to have 10 factorial, because that's my n, divided by 10 factorial minus 0 factorial. I know, just 10, I'm sorry, I put that exclamation point there way too early. 10 minus 0 factorial, and then multiply that by 0 factorial. Now 0 factorial by definition is 1. So make sure that, when you don't always assume like, oh, you can't divide by 0. That's not dividing by 0. This is 10 factorial divided by 10 factorial times 0 factorial. This whole thing simplifies down to 1. Then what we do is we multiply by our 10% right there. All right, and that 10% is going to get raised to the 0 power, which also simplifies to 1. So what we have here is 1 times 1. And then we multiply by our 0.90. Okay, since I left that as 0.90 instead of just 9/10. That's going to get raised to the 10th power, because that would be 10 minus 0, which is 10. And that gives me an answer of, gives me an answer of 0.349. That answer of 35% is the chance that if I pick 10 students at random, that all 10 will graduate. Which should feel a little sobering, because that isn't very high of a percentage. With just a 10% dropout rate, there's only a 35% chance of me picking 10 students completely at random who are going to make it through this graduation. And that's really tough. That's really tough. Okay, so let's look at another example that might be a little bit more toothy, and you can dig into it a little bit. You're going to find no more than 2 who have dropped out. Okay, so what I'm going to do is, have 10 students. And I don't want more than 2 dropouts. So here's what I've got. I'm going to take 0 dropouts, 1 dropout, and 2 dropouts. All right, now, so with that in mind, I'm going to have to do 3 problems. See, I'm going to do the problems because I don't want any more than 2 to drop out. So I can have none drop out, I can have 1 drop out, and I can have 2 drop out. See, this is basically saying I want to pick a group of 10 where 8 or more graduate. So, I can rewrite it in that way. But really, it's saying I don't want any more than 2 to drop out. So I want 8, 9, or 10 to graduate on time. So this would be 8 graduating, 9 graduating, 10 graduating. But the way that I've written it, it says no more than 2 drop out. So since I'm talking about the dropout, I'm going to have to use my success as a dropout and my failure as a not dropout, because I'm focusing on these. Now you're probably thinking, well, why not just flip these 2 around? Well, if I put this at 90 and I put this at 10, then I got to test all the successes, and there's more successes than failures. I'd have to go, 0 graduate, or like 8, 9, and 10. It just would. You don't want to operate in that inverse category right there with these numbers. It's so much easier just to go straight forward with this. So we got 3 problems here. We got a problem for 0, which we've already found out, and we found out from the previous problem that's going to make about 35%. But now what we got to do is we got to operate with having only 1 dropout. So here comes that problem here. That 1 dropout is going to be a 10 factorial 10 minus 1 factorial, or 9 factorial, times 1 factorial, times a tenth of 10% to the first power, times 90% to the 10 minus 1, or the 9th power. Now, then we're going to do the situation if we want to see the probability that only 2 dropped out. Well, that's going to be 10 factorial, 10 minus 2 factorial, which is 8 factorial, times 2 factorial, times 10 to the second power, times 90 to the 8th power, or 10 minus 2. So we're going to get all these answers, and we're going to add these together. Since these are independent trials, since the third stipulation of this binomial distribution is that they'd be independent, we can add up the probabilities and percentages, and what we'll get, because this is the first, for the choosing 10 people and having no dropouts is 35%. Choosing and having only 1 dropout out of 10 is going to be, and I've computed this out already, about 40 or 39%, and then this one here to have exactly 2, this is 19%. We add all these together, and we get a total of about 93%. 93%, adding up all 3 of these parts together, 93% is having no more than 2 dropouts out of 10. So if we kind of open up the doors a little bit and saying, hey, you can pick 10 people, but we want at least 8 of the 10, 9 of the 10, or 10 of the 10 to pass, then that's going to be very probable, because you have about 93% of that happening. Now, here's a big problem. You want at least 6 to graduate. Oh my gosh. Which means that we're going to start off picking 10 students, but with 6 people graduating, that means 10 graduate, that means no dropouts, 9 graduate, which means 1 dropout, 8, which means 2 dropouts, 7, which is 3 dropouts, 6, and oh my gosh, we got basically, with 6 people graduating, we're looking at the dropouts of 0, 1, 2, 3, 4, and 5. Now you're looking at, oh my God, I have 6 problems to do. I have 6 problems to do. With 6 graduating right there, we're looking at 0, 1, 2, 3, and 4. And we're going to look at our 10 and our 90. And with 6 graduating, at least 6 graduating, then you're looking at, this is 10, 9, 8, 7, 6, and I'm actually jumped the gun a little bit. So we're looking at these 4 cases. Now, you might be saying, okay, great, I'm up for it, Mr. Anderson. I can do all of these 5 times. But there is there's a spot in the back of your book around page 700. Let me get the page number here. It's page 770, where I will show you as best as I can with the book here, where on page 770 they actually have this table. And I can kind of show you the power of the table. This is called the binomial distribution chart table. It's called table B. And what I have here is I have on the table here, on the left-hand side, and I'm sorry that the camera is a little janky to try to see this here. Okay. Sadly, this is about as good as I can make it here. This is 10% on my N chart right here. So this is where we're going to be looking. Since our probability, since we're looking at 10 people, we can then look at the top of the page here where it says 1% way at the top, and I'll have to kind of zoom in quickly here. Oh, this is not working out. I'm sorry about the video here. All right. This column here in the second column, shoot, I thought this is going to zoom in a little bit better here, but unfortunately it is not. All right, I've got to do a little angling here. All right. Sorry that this is kind of crappy on the fly. So we got 10 people in our study, and we have 10%. 10% is our pass, and what we can do is just drop down here and see that, oh my God, 349. This is what we spent time doing. Yeah, this is the pass. This is the odds that no students would fail. And then here's our 1, and here's our 2, and here's our 3, and here's our 4. Oh my gosh. 1, 2, 3, and 4, and 0. If we add up all of these, we save time from doing this problem 5 times. Now, what's the shortcoming of this table? Look, it doesn't do 15%. Here's 10% and 20%. So I picked a problem that did only 10%. So, this does lend itself very nicely to the table on page 771. And I'm sorry to get you dizzy there a little bit by moving the camera around so much, but you can see we can just copy those values from the table, which I'm going to do right now, that this is going to be about 35%. Though, only having 1 dropout is about 39%. Having only 2 dropouts is 19%. Having 3 dropouts is 57, or about 6%. And having 4 dropouts in the mix is like having about 1%. And if you add all these up, this is going to get you about 98% chance of this happening. And that might be rounded up to 99 depending on what you have for your third decimal right there. But that just shows you to having at least 6 graduate out of 10 students is a near certainty if your dropout rate's only 10%. So you're going to have at least 6 graduates. So that's setting your sights pretty low, but it's pretty much going to happen. All right, and I guess the whole purpose of this here is not to get you sick from my bad camera work, but the whole purpose was to show you that, my goodness, just with a 10% fail rate, look at how that kind of affected, to get us to a certainty. You had to at least lower your standards to 6 out of 10 making it through. Crazy, eh? All right, and finally, to draw this to a close. Here's the nice thing about standard deviations. The standard deviations and averages of binomial distributions, we can easily find the average. We can easily find the variance and the standard deviation using what we know. So here's some functions to learn and love. The average of a binomial distribution is going to be the number of trials times the success. Isn't that crazy? It's so cool. And the standard deviation is going to be the square root of n times p times q. It is so great to actually see this problem so easy compared to all the work that you could have done above. So now I'm going to basically pick something near and dear to my heart. If the 25% of the original X boxes went defective, and I did some studies to take a look and see, and then independent groups said that some of the average fail rates of the original 360 was 25%. Well, let's find the average, variance, and standard deviation in a lot of 500 gaming systems. So here my n is going to be 500. My success, well, here's the thing. My success is going to be the failure rate. And then my fail is going to be the success rate. I know, it's so funny that it's backwards, but we're looking for failure. And since we're looking for failure, our success is going to be the fail rate. Yeah, it's crazy. All right, so let's go and talk about this here. Let's get the average. The average is going to be 500 times P, which is our success rate. So that means our average failed X boxes would be 125 out of 500. 125 out of 500 will fail. Now, let's take a look at the standard deviation. So we're going to take a look at, first of all, just the variance of that, which is going to be the non-rooted form. So 500 times P times Q, and that gives us an answer of 93.8 is our variance. And then we take the square root of that, so the square root of our variance which is the square root of 93.8, gives us our standard deviations of about 9.7 systems. So what that tells me is that if we have a fail rate of 25%, we're going to have 125 broken Xboxes out of 500, give or take 10. So 135 down to 115 if we're rounding to the nearest Xbox. So send me your email, your questions. I am so sorry about having to adjust the camera for that textbook, and I just had to move the tripod a little bit. So thank you very much.